Okay, so we will resume our study of open quantum systems. And quantum noise. So today we are going to look at the third approach, which was the axiomatic approach to quantum operations. And for this, what we will do is that really it's actually good to just forget about whatever we know about quantum operations, whether it's the uh, operator sum representation or the system environment interactions. So axiomatic approach to quantum operations. So forget everything we know about quantum operations. So what we essentially mean is that instead of focusing on the operator sum representation, or the other approach, which was the system environment interactions, and we traced out the environment. Let's look at what are the physically reasonable axioms, or what can be the physically reasonable axioms on quantum operations. And then work backwards from them. So let's say I have the quantum operation on a system. So probably axiom 1 would be it's a convex linear operation. That's what we demand. And by that I mean I have a quantum operation taking a density matrix, which is really uh, a convex sum of the constituent density matrices. This gives me both these should be equivalent. So this is such a map where I have the set of density matrices rho I occurring with probability piece of I, and such a map which satisfies this condition is called as a convex linear map. So let's see why such a definition is makes sense, or it is desirable to have. So why A1? axiom 1. So, well, you can think about it yourself also. Pause a while and see why, if we have a quantum operation, then we desire that to be a convex linear map. And certainly the book Nielsen and Chuang also has an interesting take on this. So please go and read it. What I'll do is that I'll tell you intuitively what's going on. So why the convex linear map is a reasonable or desirable assumption. So let's say I have a black box, and from this black box I've got the constituents, I've got the row i's, and I am spitting out someone is giving me a state piece rows of I with probability piece of I, and then it goes to my quantum operation, and then I have the final output. So my final output is going to be this guy. Now, on the other hand, what I can do is that I can actually flip a loaded coin with a probability piece of I. I'm getting rows of I, and I'm announcing it. Okay, I'm getting this. So for that person, this is going to be this quantum operation over here. So the final outcome, the point is that the final outcome should be independent of the fact that whether or not I announce the coin flip or I do not announce a coin flip. So over here, I have just told you that this is the black box, and I am going to give you one of the consequent states with the probability piece of I. And after a long time, let's say I do this, some sort of an ensemble interpretation, I do this, I keep on doing this, I keep on doing this. So this is the final state. After the quantum operation has been applied, you're going to assign to the system. Over here, what I do, or what we jointly can do, is that we do this many times, but each time we flip a coin, and with the probability, let's say it's a dice, it's a six-sided dice if there are 6 rows of i's, and so this is sort of a Bayesian interpretation, I would say, and this is a frequentist interpretation, that I'm doing this many times. I flip a coin, I give you row I flip a coin again, I give you rows of I with some piece of I, and with piece of I, because I am giving you an input rows of I, this is the quantum operation acting on it. So whether my study is a Bayesian study or it's a frequentist study, I should have this guy. So the bottom line is that the final outcome should be independent of the fact whether or not I announce the coin flip or not. So that's the idea. Let's say, I mean, and uh, that's why I demand that finally, when I apply the quantum operation, whether or not I knew what's coming to me or I announced what's coming to me with the probability piece of I get rows of I, these guys should be equivalent to each other. So that's why we demand that uh, this convex linear map is a reasonable assumption. So the second condition, what I put on quantum operation, what's desirable, I demand the quantum operation to have is that trace should be less than equals to 1. So remember, a quantum operation can do two things, what we have studied. Quantum operation either it can take density matrices to some other density matrices, and in that case I have this guy equals to 1. That's scenario 1. Or I can model measurements. I can do a lot more. I can sort of trace out the environment. I can do all sorts of things, but these were the two things which were sort of popular. And in that case, we have seen that I have got these measurement operators. Ease of rho was given by some measurement operators, this guy, and in this scenario I had trace of ease of rho was less than equals to 1. So trace of ease of rho captures the probability of occurrence of outcome indexed by m. It is also, I think, worthwhile, by the way, mentioning that when I have a trace of ease of rho less than 1, we say the quantum operation ease of rho does not provide the complete description of the quantum process. There's something more remaining. The complete description of the quantum process. I mean, for example, we already had this guy. Well, we do not know what are the other outcomes. But on the other hand, when we have the trace of quantum operation applied upon the density matrix equals to 1, we say that the quantum operation covers all quantum processes. And finally, so these were the two axioms so far. One was, you can say, a mathematical convenience, and the other was, of course, the uh, convex linearity. Uh, there's one more thing we want from a quantum operation, and that is called as, let's say, axiom 3. It's the notion of positivity, or should we say complete positivity. What do we mean by that? So, look, the quantum operation should take a positive operator to a positive operator. So, well, why is that so? I mean, the answer is simple, that the any physically sensible state of a quantum system is a density matrix that's a positive operator. So, I have the input system, let's say this is my input system, and I have my output system. If rho is a positive operator, the output should or must operator as well. Not only that, there's a notion of, so let me call this, this is positivity and this is complete positivity. Now what do I mean by complete positivity? Let's say my system Q1 is, I have also an extended system R. It can be part of the environment, some other system, so on and so forth. So let rho QR be any operator residing in this joint Hilbert space. Be any operator residing in the joint Hilbert space. And what do? I perform a trivial operation where I perform a trivial operation I on the extension on R, the extended system And the quantum operation, same operation which I had earlier as in this guy, on the system. And this should yield a positive operator. And this should yield a positive operator. So not only a quantum operation should take a positive density matrix to a positive density matrix, the same operation applied to an extended system where I am doing nothing on the extension, and the same quantum operation on the system should also lead a positive operator. So mathematically speaking, that essentially means is that I have a trivial operation on R and the same quantum operation on the system, and this is any quantum system on the extended Hilbert space, any quantum system on the extended Hilbert space. This should give me a positive operator. This condition A3, which I would call, is known as complete positivity. So this guy over here is known as complete positivity. So as an example of something that is not completely positive, which is positive but not completely positive, let's see an example. So what's an example of an operation that's positive but not completely positive? So let us look at this operation called as the partial transpose. We have a 2-qubit density matrix, and the way the transpose acts is well, in this case we just have one density matrix, so we'll just deal with the transpose, and it gives us ACBD. And you can verify that the transpose operation preserves positivity of a single qubit. So it will take a positive density matrix to a positive density matrix. So what happens when we apply the criteria or check the criteria for complete positivity on this map? So what I'm going to do is that I'm going to apply, let's consider the state a 2-qubit state which is maximally entangled. this guy. So this is a Bell state, this is a maximally entangled state. Now what do I do is that I apply transpose to the first qubit, I do nothing on the second qubit, and I have applied to the density matrix of the Bell state. And what do I get? In terms of the density matrix jargon, I get so this has eigenvalues you can verify it, but you notice something. It doesn't take a positive operator, this guy, to a positive operator. I have one eigenvalue to be negative. So we have an example of a map, the transpose map, which is a positive operator that's not completely positive. And of course, you know, people have debated for whole long, so what's the big deal? But when we are going to study quantum operations, we are going to keep uh, three axioms, which was the trace condition, the condition of complete positivity, and the condition of convex linearity into mind, and that's going to describe our quantum operation. So now, after we have our three axioms, A1 was, let's say, convex linearity, A2 was trace of piece of rho 1, and A3 was complete positivity. We come up with the result or the theorem, a map that satisfies A1, A2, A3 if and only if you can guess what? It has an operator sum representation. So that's how we prove the equivalence of operator sum representation to the axiomatic way we have defined a quantum operation. And since we already know that the operator sum interpretation is already equivalent to taking into account the system environment interactions, all three of them are equivalent. So just write it down. This guy. So, and of course in the definition we have over here. So yeah, I just put it to be identity. Okay, so how do we show this? So well, we can go in one direction, which is, well, certainly you start from this condition. We can trivially verify that this is a convex linear maps. This map is going to act exactly the same way on a convex linear combination and is going to yield this guy to me. It's convex linear. Showing that the trace is less than equal to 1 is simple. That comes from this condition. You can check. What about complete positivity? So I had this guy A1, A2, complete positivity. How do we show that? So, well, that's also easy. Let's say I have a state of a system, some system QR, where Q was my system and R was the extension we were talking about. Now we need to show that a positive operator A on QR goes to another positive operator. So we need to show that a positive operator A on QR goes to another positive operator upon action of this guy, where I do nothing to R. See, I'm using either R as the first system and the system as the second system interchangeably. It doesn't matter as long as I keep the order of my tensor product on operators same as what I'm keeping on the states. So bottom line is that any extension, a positive operator A on the system QR should yield another positive operator when I do nothing to the extension extended system and I operate the same quantum operation on system A. So that's what I need to show. So I have a state which applied on this guy where this was my operator sum element. So I can see that the inner product with respect to the state, and I have an operator A, a positive operator by the way, and I am doing nothing to this guy, the R system, and I am operating the parent system by an operator sum representation. So that yields me nothing but which is greater than 0 since A was a positive operator. So if this is true for a single I, well, this is true in general. So what I have is just the sum of these guys, and that's going to give me something greater than 0. So the bottom line is that I started with a quantum operation with an operator sum representation, and I had to show these three properties: convex linearity, the trace condition, and complete positivity. So by complete positivity, I wanted to show that a positive operator A on the system as well as interaction goes to a positive operator upon the action of the following quantum operation, where I do nothing to the extension and I apply the same quantum operation given by, remember, this guy was given by this guy, and that's exactly what I've showed over here. I defined some vectors which would be mapped from my initial vector by the following quantum operation, and I showed that such an operation takes a positive operator to another positive operator, and if it is true for one of the I indexes, this is true for the sum, and that's how I showed that this guy, this operation applied on a positive operator gives me something which is positive. Okay, so now how do we prove the converse? Right now we have proved that given I have a quantum operation this guy, this leads to my three axioms. Now let's assume we have an operation satisfying A1, A2 and A3, and we ask the following questions: under what conditions one can find operator sum representation? So remarkably, if we know the action of the operator, this is kind of a tricky. So in some sense, what we are proving is that let's say we have a quantum operation satisfying these three conditions: convex linearity, complete positivity, and the trace condition. Then, yeah, I mean, this is, there will be several quantum operations satisfying this. What we are really interested is in that, can we find a very specific operator sum representation under certain conditions? And it turns out that, and it's quite a remarkable thing that if we know I'll just write it down. Remarkably, if we know the action of the quantum operation on the maximally entangled state of a system and its mirror system, then we can find it. So I'll just write it down and it will be more clear to you guys. If we know the action of the operation on an extended system consisting of the maximally entangled state. That's it. That will do. So what do I mean by that? I mean a specific operation on the maximally entangled state. I'll say this is, so I have, let's say alpha was my maximally entangled state. I had a system, a reference system and my original system. Remember, this is Schmidt basis and I'm neglecting the normalization, but this guy, if you notice, this is the maximally entangled state. This is the state for 2 qubits. This would be of the form 0, 0 plus 1, 1, something like that. So this is the maximally entangled state alpha. So if I know the following operation, I do nothing to the R system. I apply the same quantum operation to my parent system, and I am doing this on the maximally entangled state. So once we know this guy, I'm going to drop the subscript here. We know it's implied that this is going to be applied on the maximally mixed state. So by this guy we know, I mean, we know the action of the following, where I do an identity, a trivial operation on the R system and the quantum operation I am interested in on the my principal system on this guy. We can deduce the quantum operation. That is, we know the, so what does that mean? That means that we know we can deduce means we know how epsilon acts on any state, or in other words, we know an operator sum representation of the quantum operation. So again, we'll just, how do we show that? We just write this down. This is the guy where, remember, alpha was my maximally mixed state. This guy. So now what do we do? For showing that, let's define a state in the Hilbert space of the system. So this psi j are some coefficients. So I have, again, I have the system Q and then I have the extension R. And I also define the corresponding state in the R system to be some other coefficients. Now the claim is once I take the inner product with respect to a system on R, I'll get a quantum operation on the system Q. And the claim is that that quantum operation is exactly this guy. So how do we show that? Well, it's quite easy. I have this guy and what was sigma? Sigma was the quantum operation on the maximally entangled state. So what was the maximally entangled state? So if I have alpha to be this guy, then the density matrix would be given by I some j index tensored into a similar state on the Q system. This is just the outer product. So I'm just expressing my quantum operation sigma on the maximally entangled state in terms of this guy where I do nothing to the system. So this state retains itself over here exactly the same, and I am applying the quantum operation over here. So what do we get after simplifying this guy? Remember, to simplify this guy, I also need to remind myself that this state was given by these guys. That's how I define these quantities. So when I plug this back over here again, I will get the quantum operation on system Q weighted by these coefficients. I forgot where is the which one is the complex conjugate. So yeah, so this guy. One of them comes from here. This guy, and the psi j star would come from here. And lo and behold, this is nothing but the quantum operation on the state the state. So that part is clear. We have shown that what we were set out to do, that certainly once I know this operation on the maximally entangled state of the system, as well as you can call it a mirror system on an extension, then just I know it on the maximally entangled state, and then tracing out gives me, remember this was the most general, any state in the Hilbert space of the system, I'll know the quantum operation on the system. What about the operation elements? So finding the operational elements, right now I've just shown that if I know the quantum operation on the maximally entangled state, then I know the quantum operation on any damn state of the system. So the finding the operational elements, let's assume that my quantum operation was, I'll have some sort of a spectral decomposition of this quantum operation, and let me define an operator on the state of the system which is given by this guy. And I claim that this is exactly the operator elements I needed on the parent system. And why is that so? Well, you can already check that I'll have to write it explicitly, but let's see what this quantity yields me. Remember, these are the operators on the system, as I have taken the inner product of the whole thing with something on the environment. So I traced out the environment in a way I get an operator on the system. So this guy is nothing but, if I can write it down in terms of the outer product as I had defined this guy. So I'll have this guy psi r, just plugging in this definition here, actually here. This guy. And what is this? This was nothing but my quantum operation. So I have nothing but or this guy. This was already proved above that this is nothing but this guy. So in other words, my quantum operation was nothing but, in terms of my operator sum elements, this guy, where each of this guy was defined as in terms of this guy, where beta was nothing but the sum decomposition of the operator on the maximally entangled state. So what's the point of the long-winded argument? Well, the long-winded argument, the point was to show an equivalence between either I start from the operator sum interpretation of the quantum operation, that's what we did here, and then slowly worked our way. So these were the three conditions we showed that starting from an operator sum representation, these guys hold. That's what we showed here. And then the other point was that I assume that a map will have these three conditions. A map will be completely positive, a map will be have a trace condition, and the map will be convex linear. We showed that if we know the action of such a map on the maximally entangled state of a system and an extension, we would know its operator sum representation. So that's what we set out to do, and we showed this in this thing. As a final thing, what do we, yeah, so by the way, we have shown this is a minor point left. We have shown this guy to be equivalent to some operator sum representation. We can extend this to by convex linearity. To anything, any sorts of, not only a density matrix which is this guy, but any row prime we can show over here. So as a last topic, which is also kind of important, is that does a quantum operation has a unique operator sum representation? Or one can paraphrase this question also as freedom in operator sum representation. Think about it. So, given a quantum operation, these guys, can two different set of quantum operation elements give rise to the same density matrix? That's another way of putting this question. Quantum operator operation elements. Give rise to the same density matrix. So consider the example. I have an operator sum representation where I have these guys as elements. And the other element is The other quantum operation I have is with the following. This guy and an F2. And this is just the projector. 1, and you guessed it, this is just the projector 0. So you can see these are, even in nature, they are two different operator sum elements. One is an identity and something to do with the z, the phase thing, and this is a projective measurement, 0, 0 or 1, 1. So they represent different operational elements, but if you notice, F1 is nothing but E1 plus E2 divided by 2 divided by square root of 2, and F2 is E1 minus E2 divided by square root of 2. And if you look at what happens when I apply a quantum operation with these operational elements F1 and F2, I get, I just write them down in terms of E1 and E2. I dagger them plus the whole divided by 2, and that's nothing but equivalent to E1 row E1 dagger plus E2 row E2 dagger, nothing but our quantum operation. So it was the same quantum operation. Which is kind of interesting that I can have the same quantum operation, but the operation elements appearing are not unique. So in order to understand what's the source of this freedom, how this freedom is coming, let's say from a diagram, I have an environment, a system. This is the environment starting in some state. That was our diagram. And no matter what I do to the environment here through some unitary, and I can make a measurement, I'll get the same quantum operation on the system. So there's a unitary freedom in what I do with the environment. Because ultimately I have to trace out the environment. And it does not change the quantum operation on the principal system. And how does one capture that? Well, the new projection elements Fk, or I should say the new operation elements, new operation elements are related to doing nothing on the system, some unitary on the environment, and then tracing out the environment as we do. and I can insert an identity here. So I'll get I can take this summation out, or in other words, I have this guy was the old operation elements. So the new operation elements are related to the old operation elements by elements of a unitary matrix, where I had the same quantum operation, actually didn't matter. I'm taking it or different operation elements giving rise to the same quantum operation, and they are related to each other by elements of a unitary matrix. So with this, we I know, I mean, all this might be a bit abstract to you guys, but it's necessary to know the source of quantum noise, the interactions with the environment in a very exact quantum information theoretic way. In the next lecture and the next to next lecture, we are going to study concrete examples, or what's the application of these the quantum operation formalism, and we are also going to study the limitations of the quantum operation formalism. Thank you.